Imagine the universe as a vast, invisible tapestry, stretching in every direction, folding and curving in ways that defy ordinary intuition. This is not a metaphorical exercise. It is a literal description of the fabric of reality itself. Space and time are not separate arenas in which events unfold. They are intertwined, forming a four-dimensional continuum we call spacetime. And within this cosmic fabric, a subtle, pervasive phenomenon shapes the motion of stars, planets, and galaxies: gravity. But gravity is not what it seems in our everyday experience. It is not simply a force pulling objects together like an invisible string. Instead, it is a curvature of space-time itself, a bending and warping that guides the paths of all matter and energy. The story begins with simple observation. Objects fall, apples drop, rocks tumble, and planets orbit their stars. For centuries, this behavior was described by Newtonian physics, which treated gravity as a force acting at a distance. The law was precise and predictive, yet it offered no deeper explanation for why mass should attract mass across empty space. It was as if gravity were a mysterious messenger, instantaneous and unseen, dictating motion without revealing its own mechanism. While Newton's equations could calculate orbits and trajectories with remarkable accuracy, they left an uneasy question lingering. What truly is gravity, and how does it operate? The answer begins with the realization that space and time are malleable. Einstein's theory of general relativity reshaped our understanding, proposing that mass and energy curve the fabric of space-time, and that what we perceive as gravitational attraction is actually objects following the straightest possible paths along this curved terrain. Imagine placing a heavy ball on a stretched rubber sheet. The weight creates a depression, and smaller balls placed nearby naturally roll toward it. Not because they are pulled by an invisible force, but because the sheet itself guides their motion. In this analogy, the sheet represents space-time, and the curvature induced by mass creates the effect we perceive as gravity. Every object, from the smallest particle to the largest galaxy, interacts with space-time. The sun's immense mass bends the fabric around it, guiding Earth along a nearly circular path. Light, which has no mass but carries energy, follows these curves as well, a phenomenon known as gravitational lensing. Distant stars can appear distorted or multiplied when their light passes near massive objects, providing visual proof of space-time's warping. Gravity is thus a geometric phenomenon, a manifestation of the structure of the universe rather than a conventional force transmitted through space. Yet this curvature is subtle and pervasive. It is not always dramatic like the deep well created by a star, but it is everywhere. The Earth's mass bends space-time enough to keep the moon in orbit. The presence of mountains, oceans, and even our own bodies contributes infinitesimally to the local curvature. Every particle follows the geodesics, the straightest possible paths, in this warped space-time. Motion, then, is not dictated by a mysterious pulling force, but by the geometry of the cosmos itself. Objects move along paths determined by curvature, and what we call gravity is simply the experience of that motion. Time, intimately linked with space, is also affected by gravity. Clocks at higher altitudes tick slightly faster than those at sea level, a consequence of gravitational time dilation. This is not an abstract prediction. It is verified by GPS satellites, whose onboard clocks must account for the difference to provide accurate positioning. In strong gravitational fields, such as near a black hole, time itself stretches dramatically, illustrating that gravity is inseparable from the very flow of time. The curvature of space-time governs both the paths of objects and the rhythm of events. Gravity is not uniform. It varies depending on the distribution of mass and energy. Dense objects like neutron stars warp space-time intensely, while regions of empty interstellar space remain nearly flat. Yet even across these vast emptinesses, the gentle curvature guides the motion of galaxies, clusters, and cosmic filaments. The large-scale structure of the universe, the cosmic web of matter spanning billions of light years, is shaped by gravity, with space-time acting as the scaffold upon which matter accumulates. What appears as empty space is actually a dynamic, responsive medium, bending and flexing in response to mass and energy. Beyond the bending of light in orbits, gravity communicates changes across space via gravitational waves. These ripples, predicted by Einstein and observed directly a century later, propagate at the speed of light, carrying information about cataclysmic events such as black hole mergers. The universe is alive with these subtle vibrations, distortions in the very fabric of space-time that spread across millions or billions of light years. Each ripple is a message, revealing the dynamics of massive objects and confirming that gravity is not a force transmitted invisibly through space, but the stretching and contracting of space-time itself. Even at smaller scales, gravity plays a unique role. Unlike other forces, electromagnetism, the strong and weak nuclear forces, it cannot be shielded or neutralized. Its reach is infinite, its influence cumulative. While weak in strength compared to electromagnetic interactions, gravity dominates the structure of stars, planets, and galaxies precisely because it always attracts and never cancels out. Its omnipresence, combined with its geometric nature, makes it both subtle and powerful, shaping the universe over eons in ways that are both predictable and awe-inspiring. The quest to understand gravity leads inevitably to questions about its fundamental origin. Is space-time itself emergent, a manifestation of deeper quantum phenomena? Could there be particles, like hypothetical gravitons, mediating gravitational interaction in the quantum realm? Modern physics seeks to unite general relativity with quantum mechanics, probing the microscopic structure of space-time and elusive nature of gravity at the smallest scales. While the equations of relativity describe how space-time curves, they do not explain why space-time exists or why it responds to mass in the way it does. These remain among the deepest mysteries of science. Our perception of gravity is intimately tied to our everyday experience. We feel it as weight, as the pull that keeps our feet on the ground. Yet this familiar sensation is only a local manifestation of space-time geometry. On cosmic scales, gravity orchestrates the dance of galaxies, governs the formation of stars, and guides the expansion of the universe itself. It is a force we cannot touch directly, but one that shapes all motion, all structure, and the very flow of time. In essence, gravity is the story of space-time itself. Mass and energy mold the geometry. Curvature dictates motion, and the universe unfolds according to these rules. What we feel as attraction is simply our experience of moving through curved space-time along natural paths. The deeper we probe, the more we realize that gravity is not a substance, a particle, or a force in classical sense. It is a language of space-time, the rule-book of motion, and the invisible framework that holds the cosmos together. As we move deeper into the nature of gravity, we find ourselves venturing into realms where intuition falters and the universe reveals its most subtle secrets. While general relativity describes gravity as a curvature of space-time, it leaves open one of the most profound questions in physics. What is gravity made of at its most fundamental level? Unlike other forces, such as electromagnetism or the strong nuclear force, which are mediated by particles like photons or gluons, gravity resists easy classification. It is both everywhere and nowhere, pervasive yet intangible, shaping reality without a tangible form we can grasp. Modern physics suggests that gravity might ultimately have a quantum foundation, a connection to the microscopic world where space-time itself could be composed of discrete elements. In this view, space-time is not a smooth continuum but a granular, foamy structure at scales far smaller than anything we can directly observe. This concept is at the heart of approaches like loop quantum gravity, which proposes that space-time is built from tiny loops woven together in a dynamic network. In such a universe, gravity emerges as a macroscopic effect of these underlying quantum threads, guiding motion without ever existing as conventional substance. At the same time, theorists explore the possibility of gravitons, hypothetical quantum particles that mediate gravitational interactions in a manner analogous to photons for electromagnetism. If gravitons exist, they would carry the force of gravity across space-time, yet they remain undetected, elusive because their interactions are unimaginably weak compared to other fundamental forces. Detecting gravitons will provide a direct link between the quantum world and the geometric description of general relativity, bridging two realms of physics that have remained stubbornly separate for over a century. Gravitational waves offer a remarkable window into this hidden dimension of gravity. These ripples in space-time, produced by colliding black holes or neutron stars, travel vast distances at the speed of light. They do not merely inform us about the events that created them. They also demonstrate that gravity is a dynamic, propagating phenomenon, not just a static curvature of space-time. Observatories like LIGO and Virgo have confirmed these waves, revealing that the universe is alive with the vibrations of space-time itself. Each detection is a testament to profound reality that gravity is woven into the very structure of existence, capable of carrying energy and information across incomprehensible distances. Black holes illustrate gravity's extremes with unparalleled drama. Within a black hole's event horizon, space-time curves to an almost infinite degree, and our classical understanding of gravity reaches its limits. Time slows near the horizon, space stretches, and tidal forces become extreme. The singularity at the center represents a point where our equations break down, signaling that a deeper, quantum theory of gravity is necessary to fully understand what gravity is and how it behaves under these conditions. Black holes are natural laboratories, where the geometric picture of gravity meets the unknown quantum realm, challenging our conception of the very nature of reality. Gravity's subtlety is further highlighted by its weakness relative to other forces. Electromagnetism, the strong nuclear force, and even the weak nuclear force dominate interactions at small scales, yet gravity rules at the cosmic scale. Stars, galaxies, and clusters of galaxies are bound together by gravity alone, even though the same particles involved could be influenced much more strongly by electromagnetic forces. This apparent paradox emphasizes that gravity is not a traditional force mediated by direct contact or exchange. It is a structural property of space-time, cumulative and persistent, shaping the universe's architecture across unimaginable distances. The quest to unify gravity with quantum mechanics drives much of contemporary theoretical physics. String theory, for example, posits that all particles, including the graviton, arise from tiny vibrating strings. In this framework, gravity is an emergent phenomenon arising naturally from the vibrational patterns of fundamental strings, linking the macroscopic curvature of space-time to an underlying microscopic order. Although these ideas remain speculative, they provide a tantalizing glimpse of reality in which gravity is not simply an effect, but a manifestation of a deeper, unified structure of matter, energy, and space-time. Even in the observable cosmos, gravity shapes the grandest structures with elegance and consistency. Galaxies rotate, stars form and collapse, and cosmic filaments stretch across billions of light years, all guided by the invisible hand of space-time curvature. Dark matter, an unseen component inferred from gravitational effects, further emphasizes that what we perceive is only a fraction of reality. Gravity operates on both the visible and invisible, orchestrating motions and structures that span the universe, suggesting that understanding its true nature may require looking beyond ordinary matter and energy. Experimental efforts continue to probe gravity at ever finer scales. Laboratory experiments test the inverse square law of gravity, search for deviations that could indicate extra dimensions, and explore phenomena predicted by quantum theories of gravity. These experiments aim to uncover clues about what gravity is made of, whether space-time is continuous or discrete, and how it connects with the other forces of nature. Each measurement, each observation, brings us closer to a deeper understanding of the most pervasive phenomenon in the universe. At the human scale, gravity shapes our daily experience in ways so fundamental that we rarely question them. It gives weight to our bodies, anchors oceans, guides rivers, and orchestrates the cycles of the seasons. Every step we take, every object we lift, is governed by curvature in space-time, a geometric reality that underlies even the most mundane interactions. Yet these everyday effects are just a hint of the complexity and profundity hidden beneath, where quantum phenomena, cosmic structures, and the very flow of time converge. Understanding gravity is not just a scientific pursuit. It is a philosophical journey. It challenges us to rethink what we mean by force, matter, and space. Gravity is at once familiar and alien, intimate and cosmic, simple in its everyday effects yet profoundly complex in its origin. By exploring its mysteries, we explore the architecture of reality itself, gaining insight into how the universe functions and how we are connected to its vast, invisible fabric. Next, we will examine gravity on a cosmic scale, its role in shaping galaxies, driving the expansion of the universe, and interacting with dark matter and dark energy. We will explore how gravity is not only a local phenomenon, but a fundamental principle that structures the entire cosmos, revealing the hidden dynamics that govern the largest scales of existence. As we step back to view gravity on the grandest scales, its influence becomes even more profound. Gravity is not merely a local phenomenon, pulling apples to the ground or keeping planets in orbit. It is the architect of the cosmos. Galaxies form, spiral, and collide under its guidance. Clusters of galaxies gather and interact because of it. Filaments of matter stretch across hundreds of millions of light years, forming the cosmic web. In every corner of the universe, gravity leaves its signature, shaping structure and motion in ways both subtle and dramatic. Understanding gravity at this scale is essential for grasping not only the mechanics of the cosmos, but also the hidden components that remain invisible to ordinary observation. The role of gravity in galaxy formation is a striking example. Clouds of gas collapse under their own gravitational pull, forming stars, star clusters, and eventually galaxies. Gravity governs the rotation curves of these galaxies, dictating the orbital speeds of stars at different distances from the center. Yet observations reveal anomalies. Stars at the outer edges of galaxies move faster than can be explained by visible matter alone. This discrepancy points to the presence of dark matter, a mysterious substance that interacts gravitationally but not electromagnetically. Gravity, therefore, acts as both a probe and a ruler, revealing the unseen components of the universe through its influence on visible matter. Clusters of galaxies illustrate gravity's organizing power on an even larger scale. These colossal structures, containing thousands of galaxies, are bound together by the gravitational pull of both visible matter and dark matter. Galaxies within clusters move in complex orbits, colliding and merging over billions of years. The hot gas filling the space between galaxies emits X-rays, shaped by the gravitational wells of clusters. Gravity, in this context, is not a gentle force. It is a cosmic sculptor, guiding matter over incomprehensible distances and timescales. Gravity also governs the expansion of the universe itself. When we observe distant galaxies, their light is redshifted, stretching toward longer wavelengths as space itself expands. This expansion is not uniform in its local effects. Gravitational attraction slows the movement of nearby galaxies relative to each other, while at greater distances, dark energy accelerates the expansion. Gravity acts in opposition, and in concert with these other cosmic forces, revealing a delicate balance that governs the evolution of the cosmos. Without gravity, galaxies could not form, stars could not ignite, and the universe as we know it would not exist. Black holes, the most extreme manifestations of gravity, provide both awe-inspiring phenomena and natural laboratories for understanding the limits of physics. Their gravitational pull is so strong that not even light can escape. Once it passes the event horizon, matter falling toward a black hole is stretched, compressed, and heated in ways that produce spectacular jets and radiation. Observations of these objects, including the imaging of the black hole at the center of the M87 galaxy, confirm predictions of general relativity to astonishing precision. Yet black holes also highlight the incompleteness of our understanding. The singularity at their core remains a region where gravity, spacetime, and quantum mechanics intersect in ways that challenge the limits of current theories. Gravity is intimately tied to cosmic evolution. In the early universe, tiny fluctuations in density, magnified by gravitational attraction, seeded the formation of galaxies and larger structures. Over billions of years, these small perturbations evolved into vast filaments, walls, and voids that define the large-scale structure. Gravity organizes matter into patterns that are both intricate and consistent with the predictions of physics, linking the microscopic fluctuations of the early universe with the grand architecture we observe today. The search to understand gravity also drives the quest for a theory of everything, uniting general relativity with quantum mechanics. While relativity explains gravity at large scales, quantum theory governs the microscopic world. Reconciling the two requires new ideas, extra dimensions, quantum spacetime, or string theoretic constructs that integrate gravity as a fundamental aspect of particle physics. Each approach seeks to answer the ultimate question: what is gravity truly made of, and how does it emerge in the underlying structure of reality? Even if a definitive answer remains elusive, these efforts reveal the richness of the problem and the depth of the universe's design. Gravity also connects to the mysterious phenomena of dark energy, which drives the accelerated expansion of a universe. While gravity pulls matter together, dark energy appears to push space apart, creating a dynamic tension that defines cosmic evolution. Understanding this interplay is one of the greatest challenges in modern cosmology. Gravity is not just an attractive force. It is part of a complex cosmic dance that shapes the fate of the universe, linking the visible, the invisible, and the unknown. At the human scale, the effects of gravity are subtle but profound. Tides, planetary orbits, and stability of Earth's environment all result from gravitational interactions. Even the light from distant stars bends as it passes massive objects, subtly influencing our observations and understanding of the cosmos. Gravity is the silent stage director, orchestrating motion, shaping history, and governing the evolution of matter from the smallest scales to the largest. In practical terms, understanding gravity enables exploration and technology. Satellite trajectories, GPS systems, and space missions all rely on precise knowledge of how gravity bends paths and slows or accelerates clocks. Even as we grapple with cosmic mysteries, gravity informs our daily lives, linking abstract theory with tangible reality. Its presence is constant, yet its complexity invites continual study, discovery, and awe. The interplay between gravity, dark matter, and dark energy reminds us that what we observe is only a fraction of reality. Gravity acts as a cosmic messenger, revealing hidden structures and guiding us toward deeper truths. Every star, galaxy, and cosmic filament follows its influence, demonstrating that gravity is not merely a local or terrestrial phenomenon, but a fundamental principle shaping the entire universe. Finally, we will reflect on the philosophical, technological, and scientific implications of understanding gravity. We will explore how gravity connects the smallest particles with the vast cosmos, and how ongoing research continues to push the boundaries of human knowledge, moving us closer to answering the ultimate question: what is gravity truly made of? As we arrive at the final stage of our exploration, gravity reveals itself not merely as a force or phenomenon, but as a profound lens through which we understand the universe. It connects the very small to the unimaginably vast, guiding particles, stars, and galaxies alike, shaping the evolution of the cosmos, and influencing the passage of time itself. The question of what gravity is made of remains one of the deepest in science, a mystery that links general relativity, quantum mechanics, and the very structure of space-time. Through this inquiry, we come to see that gravity is both simple and complex, tangible in effect but elusive in origin. At its core, gravity is a curvature of space-time. Mass and energy bend the fabric of the cosmos, creating pathways along which objects naturally move. We experience this daily as weight, yet this mundane sensation belies the extraordinary implications of curvature on cosmic scales. Stars orbit galaxies, galaxies cluster together, and light itself bends around massive objects. Gravitational waves ripple across space, carrying information about collisions and cosmic cataclysms, while black holes stretch and distort space-time in extreme ways. Gravity is the silent sculptor of the universe, shaping both the seen and the unseen, the ordinary and the extreme. Yet, as we look closer, questions arise that challenge the completeness of this geometric picture. At quantum scales, gravity remains enigmatic. Unlike electromagnetism, the strong and weak nuclear forces, there is no confirmed quantum mediator for gravity, no detected graviton. Space-time itself may be discrete, a granular network of fundamental units that produce gravity as a macroscopic effect. Theoretical frameworks like loop quantum gravity and string theory propose that gravity emerges from deeper layers of reality, where space, time, and energy are interwoven in ways we are only beginning to understand. These approaches suggest that gravity is both a fundamental force and an emergent phenomenon, bridging scales from the subatomic to the cosmic. Gravity also interacts with components of the universe that remain invisible and mysterious. Dark matter, inferred solely through its gravitational influence, shapes galaxies and clusters, holding cosmic structures together. Dark energy, seemingly opposite to gravity, drives the accelerated expansion of space, creating a tension that defines the universe's long-term evolution. In this interplay, gravity is not a solitary actor, but part of a cosmic ensemble, guiding matter, responding to energy, and revealing the hidden scaffolding of reality. Through its influence, we gain indirect access to phenomena that cannot be observed directly, making gravity a powerful probe of the universe's deepest secrets. Philosophically, gravity challenges our intuition about reality. It teaches us that the familiar sensation of weight is a manifestation of something far larger and more profound, the shape of space-time itself. It reminds us that our everyday experiences are local glimpses into a much broader cosmic order, governed by principles that operate on scales we cannot fully perceive. Gravity is both universal and intimate, connecting the movement of galaxies with the falling of an apple, uniting the vast and the personal within the same fundamental framework. Technologically, our understanding of gravity has transformed human life. Satellite navigation, space exploration, and predictions of planetary motion all rely on the precise modeling of gravitational effects. Experiments like LIGO detect the subtle ripples of gravitational waves, providing insights into events billions of light years away. Even atomic clocks, essential for global positioning systems, account for the time dilation caused by Earth's gravitational field. Through these applications, the abstract geometry of space-time becomes a practical tool linking fundamental physics with everyday experience and cutting-edge technology. The ultimate nature of gravity continues to elude us, inspiring research and imagination. Scientists ask, is gravity truly fundamental, or does it emerge from deeper quantum phenomena? Can we reconcile general relativity with quantum mechanics to form a theory of quantum gravity? Could space-time itself be a manifestation of entanglement or information? These questions drive the frontiers of physics, bridging theory, experiment, and cosmic observation. Each discovery peels back another layer of the mystery, revealing that gravity is more than a force. It is a key to understanding the structure and origin of the universe itself. Reflecting on gravity's role in the cosmos provides a sense of scale and wonder. From shaping the intricate orbits of planets to governing the evolution of galaxies over billions of years, gravity is a connective tissue of reality. Its influence spans all scales, from the tiniest particles to the grandest cosmic filaments. The deeper we probe, the more we realize that understanding gravity is not just a scientific challenge, but a journey into the essence of existence. It links matter, energy, space, and time in a tapestry whose threads we are only beginning to trace. Ultimately, the question of what gravity is made of may remain partially unanswered, yet the pursuit itself illuminates the cosmos. Gravity is at once familiar and mysterious, subtle yet powerful, tangible in effect yet elusive in origin. It governs motion, structures matter, shapes time, and reveals the universe's hidden order. By studying gravity, we gain insight into mechanics of reality, the unseen scaffolding of the cosmos, and the deep principles that unite the very small and the unimaginably large. It is a force that defines existence, a phenomenon that inspires wonder, and a mystery that drives human curiosity toward ever greater understanding. In the end, gravity is not just a force to be measured, calculated, or observed. It is a fundamental story of the universe, a silent architect that orchestrates a dance of matter and energy across space and time. From falling apples to colliding galaxies, from black holes to cosmic expansion, gravity shapes the stage on which all reality unfolds. While we continue to seek its ultimate origin, every discovery, every observation, and every insight brings us closer to understanding the invisible threads that weave the cosmos together. Gravity is a universe made tangible, the geometry of existence, and the ultimate enigma that challenges, inspires, and defines us.